our final video involving implicit differentiation for now, we're going to explore not only dy dx, the first derivative, but also the second derivative. As AP Calculus AB students, you're responsible both for first and second derivatives when deriving implicitly. Now, we know what the second derivative looks like. That's our d2y dx2, which you see on the paper in front of you. We'll talk about how to get that in a second. But first, we can't get the second derivative unless we have the first derivative. So let's start with example 31, and let's get dy dx. Okay, so we see y squared plus 3y equals 2x squared plus 1. I would encourage you at this point to pause the video and see if you can derive this one on your own, and then unpause it and see if you've caught up and you've matched with what I'm about to put on the board. So we have y squared, which we've derived before, and we know it's going to be 2y dy dx. And we have plus 3y, so plus 3, because 3x would derive to 3. So 3y will derive to 3, but again, it needs a dy dx. And then on the other side, we have 2x squared. We've been deriving that forever. That's 4x. And the derivative of a constant, in this case, the constant's 1, will be 0. So there's our derivative line, if you will. Now we've got to solve for dy dx. We have the two dy dx terms on one side. We have the non-dy dx term on the other side, so we don't need to do any moving around. We can go right to factoring out that dy dx. So let's factor out the dy dx. So we have dy dx, and then we have 2y left over when we divide out in the first term. And we have plus 3 left over for the second one. And that's still equal to 4x. And now we can solve for dy dx by division. So we have dy dx is equal to 4x over 2y plus 3. There's our first derivative. Not too bad. Hopefully this is starting to become a little easier for you to work your way through. You have some practice on the assignment as well. But we're not quite done yet. This is dy dx. We want to find the second derivative. We want d2y dx2. So let's take this. I'm going to transfer it over to what you see behind me. And I've got 4x over 2y plus 3. Now I want the second derivative. The way that I get the second derivative is I derive the first derivative. Actually, you know what? Let me change colors here real quick. Get rid of this here. I'm going to take the derivative with respect to x of the first derivative. Okay? And if I do that on the left side, which I'm allowed to do, then I get d2y dx2. Right? Don't I have two d's and then the two dx's? So there's my second derivative. So I already know that my second derivative is all alone and all by itself on the left side of this equation. What goes on the right side? Well, because this is an equation, if I derive the left side with respect to x, I also have to derive the right side with respect to x. Which means I got to take the derivative of that term right there, which I can do. And notice that this is 4x divided by the quantity 2y plus 3. What was the key word that I just said? Divided by, right? Divided by means that we have a quotient, which means we have to use the quotient rule. 98% of the problems in which you ever have to find d2y dx2 with implicit differentiation are going to require you to use the quotient rule. Not every one of them, but most of them will. So let's do our quotient rule here. We're going to derive this with respect to x. So quotient rule says, put the bottom d top minus top d bottom all over bottom squared. That's how we're remembering it. That's how it rolls off the tongue. So it's denominator times the derivative of the numerator, and the derivative of 4x is 4. Okay, no dy dx's because we did not derive a y term. Minus, now we keep the numerator, and we derive the denominator. The derivative of 2y plus 3, well, 2y, that's going to derive to 2 dy dx. 3 derives to 0. So we have 2 dy dx. All over the bottom squared. All over 2y plus 3 wrapped in parentheses and squared. Now we're not going to expand this at all. In fact, we're not going to do very much with this. We're almost done. Our goal was to get the equation for the second derivative. And we have that just about, but we want the second derivative in terms of x and y. Well, this is in terms of x and y. The denominator is in terms of x and y, but this is not in terms of x and y. It's in terms of x and dy dx. So we need to somehow eliminate that dy dx. Well, up here, if you ignore the purple, notice that dy dx is equal to 4x over 2y plus 3. So our final step here is going to be to sub dy dx out of our second derivative and bring what it's equal to, 4x over 2y plus 3, into the second derivative. So our final answer, if you want to simplify this, you can. I'm not really concerned with that, but we have 2y plus 3 times 4, yes, that is 8y plus 12, minus 4x times 2 times, and then dy dx out, 4x over 2y plus 3 is in, and that's all over 2y plus 3 squared. Okay. Keep in mind that we cannot cancel this 2y plus 3 with one of those. It doesn't work that way. This entire numerator is one expression, so we can't just cross out. Leave it like this. We're done. We got it. Okay. On the exam, if you're required to do d2y dx2, which you're not always going to be required to do that because it does take some time, but if you are required to do it, it's quite possible that they'll have you find the second derivative at a point. So they'll say at the point when x is 1 and y is 2 or something like that. I don't even know if that's on our equation here, but in which case you'd plug in 1's for all the x's and 2's for all the y's. Okay, if you're trying to find just the general term, well, there it is. Stop right there. Don't simplify anymore. But do make sure that you sub dy dx out and the expression for dy dx in.